Welcome to Session 10, our second session on repeated measures in longitudinal data analysis, and our final lecture of the semester. So we're going to learn today what are mixed effects models and also population average models. You'll learn some model diagnostic plots for random effects models. You'll learn to interpret random intercepts and random slopes, to define and perform population average models, and define your choices of assumptions on correlation structure and hierarchical models. And finally, to have some options for choosing between hierarchical modeling strategies. We'll start with a review of that fecal fat dataset that we were analyzing in the last lecture, and review some potential non-hierarchical approaches to analyzing data like these before going into mixed effect models. And after introducing mixed effects models, I'll introduce another data set that's a little bit more complex, an example of longitudinal data in this Georgia Birthweights data set. And then finally, we'll cover population average models and fitting them using generalized estimating equations. And this is all continuing in the Fittinghoff textbook, chapter 7. Starting with our review of the fecal fat dataset, recall that this is a dataset of participants who lack digestive enzymes in the intestine, causing bowel absorption problems that are indicated by excess fat in the feces. And it was a study of a placebo and several different pancreatic enzyme supplements to alleviate the problem. So this data set provided measurements of fecal fat quantity in grams per day for individuals given the placebo and 3 different types of pills. So it is a perfectly balanced data set. We have 6 subjects and we have 4 measurements on each subject. And we saw before that there does seem to be an effective treatment, particularly with the tablet and capsule delivery. We see quite a bit lower average amount of fecal fat than with the placebo. And then this third treatment, the coated tablet, seems somewhat less effective and more similar to the placebo. But this box plot representation, we discussed this as being a somewhat lacking visualization because you can't see from this which are the repeated measures of individuals. So this so-called spaghetti plot helps us to do that. And here we can see that this dotted line is one individual that had a measurement of more than 70 in the placebo that went down to about 25 with the tablet and capsule and back up to close to 70 with the coated tablet. And we see this U-shaped pattern for many of the individuals, and you get this idea that there's a big difference from one individual to the other, but for all of them there appears to be some effectiveness of the treatment, especially for tablet and capsule. And so for this data set with only 6 individuals, this is a very nice visualization of it. This can get a little bit messier when you have many individuals, but it works well here. These are the big categories of analysis strategies that you can consider and that we're going to discuss. The first is fixed effects models and other non-hierarchical strategies, and we'll discuss this some more today. The second is random or mixed effects models, where the model contains certain coefficients such as intercepts or coefficients or slopes that are random variables instead of fixed variables, meaning that we assume that the population has one fixed value for them, as we have done up until now. And then finally, population average models, or you may see them referred to by a method used for fitting them, generalized estimating equations. You might also hear them referred to as marginal models. All right, first let's discuss some non-hierarchical analysis strategies, which can work. One is to look at an analysis for each subgroup, such as in that case to look at each patient independently. It doesn't work at all in this example because we only have one set of measurements for each patient, and all you would see would be like one line of that spaghetti plot for one patient, and we wouldn't be able to do much statistical analysis with that. We might be able to visualize that way as we did with the spaghetti plot, but it's not an integrative analysis. This could sort of work in an example where you had just, say, 2 or 3 doctors and many patients. So if you had just a couple of groups so that you're not likely to be able to do a statistical analysis across groups anyways, then this might be a reasonable approach. A second approach would be analysis at the highest level of the hierarchy, meaning summarize the data to the highest level, such as by the mean. So in this example, it would mean taking the mean for each participant, which doesn't work at all because it's 4 different treatments for each participant. But you could imagine that if these were just repeated measurements and you had, say, 2 or 3 or 4 repeated measurements under the same treatment for each patient, then maybe you could do it. You could just average those together and go ahead. And that can work in some cases with a few patients, say per group, such as doctor and many groups. However, even in this case, you would probably benefit from using a hierarchical model, because if you had different numbers of measurements for each patient, then you would have different precision on those measurements, and you would be able to account for that in a hierarchical model in a way that you couldn't if you were simply taking the mean and analyzing at the highest level in the hierarchy. Then there's an analysis on so-called derived variables. In this example, it would be considering each treatment separately and taking the differences in fat levels between treatment and control for each patient and using paired t-tests. So that would work in this case. You could do one t-test for each of the 3 treatments where your derived variable is the fat measurement on treatment minus the fat measurement on placebo. So it would work here, but it would not work for unbalanced groups. For example, if we had multiple measurements under some of the conditions, that would be relatively easy to account for in a hierarchical model, but not using derived variables. I mean, you could, I guess, first do averaging and then differences, but it would be a lot of work and not making full use of your data. And then finally, in some instances, like we discussed yesterday, you can use fixed effect models. And in the fixed effects models, we treat the differences between patients as fixed rather than random. So each new patient that came into the study would have a different, let's say, baseline amount of fecal fat, but that is not drawn from a random distribution. It's just some fixed value for each new patient, which may not be the most intuitive way to model something like this. So in some instances, you can avoid a hierarchical analysis, even if your analysis and your model might be more intuitive and even easier to do with a hierarchical model. But there are cases where it's definitely needed and there's no way around it. One is when the correlation structure is of interest, such as familial aggregation of disease or consistency of a treatment within centers. The second is if we wish to, quote, borrow strength across the levels of a hierarchy in order to improve estimates. By this, I'm referring to something like the standard deviation of measurements on individuals at different centers, and assuming that those are the same across different groups or centers. So you can use measurements from all of your different groups to help improve an estimate that you expect to be similar or the same across all of the groups. A third is when you're dealing with unbalanced data. So if you have multiple measurements but different numbers of measurements across each of your patients or hospitals or groups. And finally, if we just want to benefit from software that is designed for hierarchical data. And once you learn how to use some of this software, you'll find it's pretty easy and similar to many of the analyses that you have done, and gets you a number of analyses in a way that are easier to do and easier to interpret than you could do on your own without using it. Okay, let's get into the first of these properly hierarchical approaches now with mixed effects models. So we're calling our two-way ANOVA analysis, this is not a mixed effects model, this is all fixed effects that we already fit for this fecal fat data set. We modeled our measurements IJ, so this was subject I, pill type J, as an overall mean. So this would be like the overall average of, or for the reference group of the fecal fat measurement, plus a subject-specific effect. So for each subject other than the reference subject, this would be the difference in means between that subject and the reference, plus another coefficient for pill type. And for each pill type other than the reference, this would be the difference in the mean fecal fat measurement for that pill type relative to the placebo, and plus a residuals term. With this assumption that the residuals are independent identically distributed with a mean 0 and a constant or homoscedastic variance sigma squared. So now with the mixed effects model, instead of fitting a coefficient beta to each individual, we'll assume that those subject effects, that is the difference in the mean measurement for each subject from the overall mean or the overall intercept, are selected from a distribution. So I'm going to call this here subject I. So compared to the two-way ANOVA, I've gotten rid of a coefficient here. There's no coefficient here for subject I. Instead, I'm not using this here as an indicator variable, but I'm using this as an actual measurement or a difference in the mean fecal fat excretion from each subject from the overall mean. And then I'm assuming that this new random variable is independent identically distributed with mean 0 and variance tau 0, 0 squared. And you'll remember that this sigma epsilon squared and this tau 0, 0 squared were the two variances that we used in the interclass correlation calculation before. So this is what we call a mixed effects model, because the so-called true intercept varies randomly from patient to patient. So this is a random variable, this patient to patient or subject variability. But we also have a fixed coefficient for treatment. So this beta for pill type J is not a random variable. In the population, it is assumed to be fixed. That is the same for everyone. So I'm just going to go ahead and fit this mixed effects model now using a package called NLME, noting that the LME4 package is another popular alternative. I don't really have a good feeling for which of these is better. They each have some strengths. LME4 might be, I think it is better documented, and it is the more modern of these two packages. NLME is pretty old school, but it's been around a long time, and it's very flexible and implements, both of them implement probably everything that you would need. but both of them are quite simple to use for a simple example like this. So all I have to do is I actually have to specify two model formulas here. The first is for the fixed effect, so I'm describing fecal fat as predicted by pill type. Specify my data, and then I have to specify this other argument which specifies what the random variables are here. And here I only specify the right-hand side because the left-hand side has to be the same as above. And what this says is that the intercept varies randomly with subject. And in some cases, you can also model with this some coefficients, such as the coefficient of pill type as a random variable. I found it actually doesn't work in this case. It's an overspecified model if I try to treat pill type as a random random variable. So I just treat the intercept. So this would be like the baseline fecal fat excretion as a randomly varying quantity per subject. So just looking at the output from this, I just typed in the object here. This isn't even the summary value. I see a number of familiar things. This is a little bit different. This REML, this stands for restricted maximum likelihood. It's not a full maximum likelihood solution, but it's used by default in these models. You can also use a full maximum likelihood. It doesn't make a difference in most cases unless you're having challenges with convergence or things like that. But you can still use this log restricted likelihood for doing a likelihood ratio test, etc. So this is showing me the fixed coefficient. So I have the overall intercept, and then I have fixed coefficients for pill type tablet, pill type capsule, and pill type coated. And if I did summary of this, I would see Wald test confidence intervals and p-values like I'm used to doing. But then there's some extra output here under random effects, and it shows me the formula that I used there. And here, it's just giving me the standard deviation of the intercept. So you recall that a couple of slides ago, we were modeling the subject effect as normally distributed with mean 0 and a fixed variance tau 00 squared. This tau 00 is what is estimated here. And then it also gives us the residual standard deviation, which is this item. So that actually then makes estimating the ICC from this output very easy, much easier than using the two-way analysis of variance like we did it last time. We have directly everything that we need. It's just this 15.9 squared divided by 15.9 squared plus 10.34 squared. And that's our estimate of the ICC. So remember, this ICC is a measure of how large the subject effect is. It's pretty large here because our subject standard deviation is actually larger than the residual standard deviation. But with these being estimated directly by the model, this becomes a relatively easy thing to estimate. There are some pretty big assumptions made in this mixed model. So the first one is something that we made before under the fixed effects models, that we have normally distributed residuals with mean 0 and homoscedastic variance. But we have an additional assumption now that we have a normally distributed latent variable. That is that this random variable of subject means is also normally distributed with mean 0 and a different variance. So this is an additional assumption that we have compared to before. And it's also somewhat of this is not a variable that we observe directly. This is a derived variable that we estimate from observations on the subjects. And with only 6 subjects here, it's not super easy to estimate this. Whereas with the residuals, we had, what did we have, 24 measurements. We only have 6 subjects, so we have 1 random intercept estimated for each subject. And this is a plot of them, of these 6. So I don't know, but it just doesn't look terrible. It doesn't look like the assumption of normality is terribly violated. But you can't really tell from this. So it really does have to be an assumption that you would have to think, is this reasonable? I think probably, like subject to subject variance of a quantitative variable like this fecal fat measurement is probably going to be normally distributed if it's not some kind of a very skewed distribution. It would help to have some background data on this to say whether that's a reasonable assumption of normality, but I don't see any alarm bells here. We can also make QQ plots, both of the residuals, and here you see that we have lots of data points. It looks like it fits quite well along this straight line, and of the random intercepts. And this also looks pretty good, so there's no great cause for concern here as to the violation of the assumption of normality. This is the output of the summary function on that fit that we performed before, and it provides some more information for us here, including the Akaike information criterion, the Bayesian information criterion, the log likelihood that we could use for model selection between nested models. Has some of this same information that we had before on the random effects. And like I promised, it has this full table for the fixed effects, including both the estimates, standard errors, degrees of freedom, the t-values and p-values from Wald test. It also has this table here for correlation, and these are estimates of the correlation between different variables. So that between the tablet data, capsule data, and coded data compared to the intercept, and it's a little hard to tell what these are. I think this is pill type tablet, and based on it not having a correlation with pill type tablet, and this is pill type P. I don't know, what is that? It's a little hard to read, but this is telling you something about the correlation structure that that has been estimated. Thinking about each of these as a different random variable. If I wanted to make this more readable, I would want to shorten the names here. And finally, within group residuals, these are the individual measurement residuals. Number of observations 24, and the number of groups 6. That's the number of patients. So it's good to review this whole thing just to make sure that it makes sense compared to what you were expecting about the number of observations, number of groups, the random effects, and the fixed effects. And this estimate of the correlations here, it's kind of interesting to see that there is an estimated negative correlation with the intercept and the 3 treatments, and a positive correlation between the treatments. So this I take to mean maybe that that individuals who have higher baseline fecal fat excretion, maybe the effectiveness of the treatment is greater for them. So they have lower observations with treatment. And positive correlations here could mean collinearity between the these variables and similar measurements between all of them. The fact that these are identical here is clearly due to an assumption being made, and we're going to talk more later about different kinds of assumptions that can be made on the correlation structure if you don't want to go with default assumptions. This is the output of a function called intervals, which is nice for this model that gives the confidence intervals for both the fixed variables. So here are confidence intervals for each of the fixed effects of treatment, and also for the random effects. So for this estimate of a standard deviation on the random intercepts, it also gives me a lower and an upper 95% confidence bound. So from this, I would say that there is evidence of variability in between patients that is not adequately explained by the random within patient variability. And this is that standard deviation of the residuals that was estimated to be 10.34, and we also have a confidence interval on that. So I'm going to go now to another example of time series longitudinal data. So in longitudinal data, we're interested in the change in the value of a variable within a subject. So in this way, it's the same as the fecal fat data set that we were just looking at, except that the data are collected repeatedly through time. And for hierarchical longitudinal analysis to be effective in this case, then these before-after measurements or measurements over time need to have some positive correlation. Here are a couple examples of longitudinal data. The first could be a measurement of sleepiness before and after administration of a treatment for sleep disorder or a placebo. A second is a study of osteoporotic fractures, the SOF data set, which is also discussed in the textbook, of women tracked with clinical visits every 2 years, and bone mineral density, body mass index, and other variables collected during those clinical data. And this is a real example of where you really cannot get by without a longitudinal data analysis, because these number of visits and the timing between the visits is not uniform over time. So there has to be a model to time fit within each patient here and summarized across patients. So a couple of example questions for this example is change in bone mineral density related to age at menopause. So here we have a time invariant predictor, age at menopause. So that is something that is a single fixed value per participant. And then we have time-dependent changes both in the outcome and in the outcome of bone mineral density. The second example is change in bone mineral density related to a change in body mass index. This is an analysis relating to a time predicting variable, a BMI, something that changes for each individual over time, with also a time-dependent outcome, the bone mineral density. And this BMI varies a lot between women and also over time. So this is a good example of analyses where you could imagine that for a single woman, for one of the women in this data set, you would be doing things like linear regression, you would know how to do it, but the challenge here is aggregating this analysis across 9,704 women to draw some more general conclusions. So I'm going to introduce this Georgia Birthweights data set on birth weight and birth order that provides birth weights and the order of infant of infants from mothers who had 5 children in Georgia. So it's a bit of an unusual data set in that all of these mothers had exactly 5 children, or at least they had at least 5, and we have data on those first 5 children. So we're interested in a couple of questions: whether the birth weight of babies changes with their order, and whether this difference depends on the mother's age at first childbirth or on the weight of the first baby. Starting with our 2 favorite plots here, here is a box plot of the data, which is, although it doesn't show the longitudinal or the repeated measurements per individual, it's quite a bit easier to read than the spaghetti plot. And here we do see that there does seem to be some trend of increasing birth weight for babies from the first, at least up to the 4th, and then maybe it's leveling off for the 5th. In the spaghetti plot, it's kind of hard to see anything other than that there's a lot of variability for each individual from one baby to the next, and it almost seems like probably that individual variability in this case looks like maybe it's larger than the between subject variability. We'll see. So if I'm right that the individual variability is higher than the subject variability, then we would have a lower intraclass correlation coefficient than we've seen before. So let's look at this question first. Is there evidence that the baseline birth weight varies by mother? That is, that the variability from one mother to another is more than the variability that could be explained just by the random variability of weights for one mother from one birth to the next. And we can answer this with a random intercept. So I'm going to fit another LME here with the outcome of birth weight as described by birth order, and with a random intercept according to this ID variable mom ID. And I found that there are not enough degrees of freedom here to also fit a random coefficient for birth order, so I'm just sticking with the random intercept. Now in this plot of the random effects, we see we have a lot more subjects in this study than we did before. And the random effects look reasonably normally distributed. We could look at the QQ plot as well, but I believe it also looks quite good for this data set, at least in terms of having a normally distributed random effect. Now looking at the summary of this fit, I can see here first under the random effects that I was right, that it seems like the residual standard deviation, that is within subject, is larger than the subject variance. So that means that we're going to have a smaller interclass correlation here. I also see in the fixed effects part of the model, intercept is not really of interest, but this coefficient here for birth order is of interest, and it tells us that on average for each subsequent infant, that infant weighs about 46.6 grams more than the previous infant. The main other thing of interest here, just seeing our number of observations and number of groups, matches with our original data set. Oh, and this correlation of our fixed effects here, not especially of interest to us, just indicates there is some negative correlation between the intercepts and the coefficient of birth order, that when you have a larger baseline infant weight, there's less of an increase with birth order, which probably makes sense. The intervals function is convenient just for giving us confidence intervals, both on the fixed effects, as we're accustomed to reporting in papers, but also for the standard deviations of the random effects. So this shows us that the standard deviation on that subject standard deviation of 367, it does not cross 0. So that is evidence for us that the baseline birth weight does vary by mother, because that subject variance is significantly greater than 0, and the variance between mothers is too much to be explained by within mother variance in birth weights. The confidence interval on the residual variance may be interesting, a little bit harder to know what to do with that. We would never really expect the within group variance to be 0 anyways. All right, now I'm going to introduce to you population average models as an alternative to random or mixed effects models that is more robust to some of the assumptions that we have to make. That is the distribution of random effects. Remember, we had to make that assumption that the random effects are normally distributed and homoscedastic, and also to assumptions of the correlation structure. That's because it estimates under this approach, we estimate correlation structure directly from the data rather than assuming normality. But this works better when you have more clusters than observations per cluster. If you only have a few clusters or groups, it's difficult to estimate that correlation structure. It also estimates our regression coefficients, that is our fixed coefficients, and robust standard errors. And this is commonly done by generalized estimating equations, or GEE. This is a method of population average modeling. Just to compare what we've done, here was one of our mixed model multiple regressions with a global intercept plus a subject random intercept, a fixed coefficient beta, with the subject intercept varying according to a normal distribution with mean 0 and constant homoscedastic variance. In the population average model, it's quite a bit simpler. It is just a linear regression where these beta 0 star and beta 1 star are population averages of the coefficients. So we're not actually even going to try to measure, for example, the standard deviation of this or of any of the other coefficients. We're just interested in that average. And these beta star are numerically equivalent for log linear and linear models if the specification of the mixed model is correct. If the mixed model is incorrect, for example, the random effects are not normally distributed, then we will get better estimates from the GEE, but not for logistic link. Fitting a population average model is straightforward. You can use this package GEE, and it's a very similar interface to everything else that we have done. One relevant thing that you will want to enter, it does have a default value, but it allows you to specify a correlation structure, and I'll talk a little bit more about what this means. But this is something that you should make a decision on based on your data set. The output from one of these GEE fits has a bunch of information about what was fit, and it has a regression table just like we are accustomed to seeing, and we see it has a very similar estimate to the estimate that we got from the mixed model, and it also has both a naive z-statistic, a robust standard error, and a robust z-statistic, which in this case are all pretty similar to each other because we don't have much in the way of outliers or departures from normality. It also gives us this working correlation structure. This is correlation between, so this is our 5 births here, 5 by 5, and you see that these values are all identical. That's what this exchangeable assumption means. I'm assuming that correlations between weights of the first baby and any other baby is the same as between any pair of the babies, no matter of their orders. So that's the correlation induced by mother is the same across all of the infants. So I mentioned you have to make some assumption about the form of correlation among grouped observations. Those options are, one is independence, so that's actually assuming no correlation between measurements within group. That's probably not one that you will often make, but you can if you have good reason to believe that the groups do not induce any correlation. Exchangeable makes sense when all pairwise correlations are the same in the population. Nothing distinguishes one member of a cluster from another. So this especially makes sense in the case of just say replicated measurements, like if you have measurements on multiple neurons from a brain, but and so they're grouped by individual, but there's no particular order to them, then this is a good assumption to make. The autoregressive assumption is that observations taken more closely in time are more highly correlated. So this assumption would be saying that you expect, say, infant 1 and 2 for their weights to be more correlated than infants 1 and 3, and for infants 1 and 3 to be more correlated than the weights of infants 1 and 4, for example. So that might also be a reasonable assumption to make here, but I don't know. In the lack of information, I might stick with the exchangeable, but I don't know in this case. Unstructured means that you just estimate a separate correlation between observations taken in each pair of times. So this is less of an assumption than the other two. So in really the lack of any information, this is a more hesitant or more conservative assumption to make. The non-stationary is similar to unstructured, but assumes that all correlations for pairs separated far enough in time are 0. So again, this assumes some sort of an ordering, but this means that any correlation between pairs of measurements, if you took enough of them far enough into time, there would be no correlation. And then stationary, an example stationary of order 2 means that observations taken at time points 1 and 3 have the same correlation as time points 2 and 4, etc. And that might be different from the correlation between observations taken at times 2 and 3. So it's like the distance or the difference in times that matters. And then finally, that correlations for observations 3 or more time periods apart would be assumed to be 0 if this is stationary of order 2. So these are a pretty flexible set of assumptions and a decision that you should make based on your understanding of what the data are, how they were collected, and how you expect them to be related to each other. In general, making fewer assumptions, such as unstructured, requires more data, but good assumptions will improve your results. This is from a paper, Mon et al., that you will have seen. It provides a list of pros and cons and help in choosing a method, and I'll just leave this here for you to look at. I won't go through all of them, but this is useful. And generally, I think that you're usually choosing between a marginal and a fixed effect model if you want a hierarchical analysis. And there are some various computational considerations to take into account and to do with the size of your groups and the number of groups. So in conclusion, ignoring within subject correlations can produce very wrong results, and it's not always conservative. You need hierarchical analysis when either the correlation structure is of primary interest, for example, familial aggregations of disease, consistency of treatment within centers, or if you wish to borrow strength across across observations at different levels of the hierarchy or across different groups, or when dealing with unbalanced correlated data. And this would be especially the truth if, well, for example, that even though that data set had exactly 5 children per mother, that really is not a requirement of the method. And finally, population average models provide a robust alternative to mixed models for one level of hierarchy. I just wanted to include a final note on reporting results of hypothesis tests, because you'll be going on now to your capstone projects and master's essays and having to write up results yourself. And there actually are there are good and bad ways to report on your results, regardless of what time or of what test you've done. As a general rule, when you're reporting results of a hypothesis test, you should include the test statistic, some measure of effect size, if relevant, such as a difference in means, something that gives like a meaning to the size of the difference you've observed, and a test name if that's not clear from the test statistic. And you should write in plain languages and let the statistics support what you're saying, not letting the statistics lead. So just for an example, and this is from this first example here of reporting common statistical tests in APA format, a good way to report a result would be the 36 study participants had a mean age of 27.4 with a standard deviation of 12.6, significantly older than the university mean of 21.2 years, where T with 35 degrees of freedom equals 2.95 and P equals 0.01. What you shouldn't do is something like this. A p-value of 0.01 indicated significant difference in age of study participants compared to all university students. So you shouldn't do this, both because you're talking about your statistical test rather than your result. So, your results are about your results, and the hypothesis test is in support of that. And second of all, you notice there's no information in this. You're saying that there's a difference. You don't know how big the difference is. You don't know in what direction it is different. And you don't have any of this information that would give some extra understanding of the test that you did. So here are a few results to help you in writing up your results. Also the Strobe guidelines for reporting observational studies. This provides a few checklists that are useful. And this third one is sort of an obscure paper, but I actually liked it a lot. It's a fair bit more detailed, I think, than either of these first two that are really meant to help you with the statistical analysis aspect of all parts of a study. Really nice little paper. So congratulations, and thank you all for your patience and for tuning in for all of these 10 lectures. Thank you.